In 10.5, we are going to be doing hypothesis testing again. This time we'll be looking at population variances or standard deviations. The reason we might want to do this type of hypothesis testing is if we are looking for consistency in some sort of produced materials, like if you're looking at medications, wanting to know if the active ingredient is consistent across all of them, or if you're manufacturing nails, half-inch nails, and you want to know make sure that they're consistent. So these are more for materials that would be produced by a factory or something like that. So we would do a hypothesis testing for variance, which is sigma squared, or standard deviation, which is just sigma. The rules are still the same. Normal hypothesis testing, we state the null and alternative. We decide what distribution we're going to use, state the level of significance, gather our data, calculate, and draw a conclusion. So hypothesis steps are the same as always. So in order to do a variance test or standard deviation, they work pretty much identically. We need simple random sample, approximately normal distribution, and we want to use a chi-squared test. I don't know that we've used chi-squared a whole lot. Chi is a Greek letter. It looks like X, so this is off. It's like a squiggly X. Okay, so chi-squared test, degree of freedom is n-1. Chi-squared distribution, here it is. Get it down so you can actually see it. It is a right skew distribution, and the higher the degrees of freedom, the more normal it is. So we don't really have to worry a whole lot about this distribution itself. We're just going to be using the table in your yellow packet or in the back of your book, just chi-squared. All right, so our test statistic for this is chi-squared equals n-1 times s squared. Remember, s squared is from your sample. Okay, this is the standard deviation from the sample. And sigma squared is from the null hypothesis. That's from the population. So that's what we'll calculate in step 3 of our test. And we will reject the null hypothesis if one of these three things is true. For a left-tailed test, if the value that we calculate is less than our critical value, we reject. For right tail, if it's more, if what we calculate is more than our critical value from the table. And for a two-tailed test, we have to find two of them. So either less than one, greater than the other. So these right here, we're looking those up in table G. The things over here are what we are calculating with the formula above, the chi-squared. And then the ones that I circled in yellow are from table G. Bad news on this is your calculator does not do this. If you look under stats and the test, there is a chi-squared test. However, that only works if you have data. They don't have an option if it's just statistics. So all of these will be done by hand. Sorry. Okay, so we have a pharmacy and they buy drug A. It's for high blood pressure. A new company has a better drug for blood pressure. They have the same active ingredient, but the new company claims that their new pill is better because the variance in the amount of active ingredient is smaller. So they're saying that they have more consistency. Drug A is known to have a variance of 0.0009. We want to test the company's claim. So there's a simple random sample of 100 new pills, and we measure the amount of active ingredient. We have a mean and a standard deviation. We actually don't care about the mean. That's not what we're measuring. Standard deviation is 0.026 milligrams. So we want to know, is this sufficient evidence at the 0.01 level of significance to support the company's claim? And we're assuming normal distribution. So let's walk through a hypothesis test on this. I need more space to write. Okay, so we're going to start with our step 1, which is stating the null and alternative. So our alternative, what we want to show is we're trying to see, is this new drug better? Is the variance actually less than the drug that we had before, drug A? So drug A was 0.0009. and we want to see, are we actually less than that? Do we have a smaller variance? So our null hypothesis is the variance greater than or equal to 0.0009. Okay, step 2, since we're doing variance, it has to be a chi-squared test. And we were told that alpha is 0.01. The equal sign just doesn't want to go. All right, step 3. We need to calculate our test statistics. This is where we're using that formula just further up on the page. Chi-squared is n minus 1. Did I do that right? N minus 1 s squared over sigma squared. Okay, n was 100 because we took a sample of 100, so we have 100 minus 1. S is the standard deviation from the sample that we took, which was 0.026. And then the sigma squared, this comes from the hypothesis test. Sigma squared is 0.0009. You don't need to square that, that's already been squared. Okay. So our chi-squared that we calculate when we plug that all into the calculator, let's see, 74.36, I believe. Okay, that's our test statistic. We need to see how this compares with our critical value. So we are doing a left tail test because our alternative hypothesis is less than, so this is a left tail. And our degrees of freedom is 100 minus 1, so that's 99. Okay, so for a left tail test, if you look up at that little table about our rejection regions, we need to find chi-squared for 1 minus alpha. Minus signs are hard. There we go. So we are looking for chi-squared 0.99. Okay, so to do this, we need to go to the table. So on your yellow paper or your fold out or whatever, it should be the last table. Make sure you're looking at the chi-squared distribution. You are looking for degrees of freedom 99. Now, the table does not go up to 99. It goes from 90 and then to 100. So normally I tell you like, oh, you should round down to be more conservative. But since 99 is so close to 100, we're actually just going to use 100. So go ahead and use the row that's degrees of freedom 100. It's close enough. And then when you look in the column that's 0.99, we should find, I don't know, 70.065. Okay, so let's draw what this looks like. So we are saying our critical value is the 70.065 for our left-tailed test. So if the chi-squared that we calculated falls in that rejection region, we get to reject the null hypothesis. Well, here's our value, and that does not fall. Our value is like up here somewhere, okay? We are not in the rejection region, so we are going to fail to reject. So let's write that down, step 4. Okay, so fail to reject. Okay, the chi-squared that we calculated, the 74.36, does not fall in our left-tailed, in that region on our left-tail test, so we have to reject. Fail to reject, I'm sorry, said that wrong. So what does this mean? Well, we can say at the 0.01 level of significance, since we failed to reject, we'll say the data does not support that the new drug has smaller variance. So at least according to our data, this new drug doesn't seem to be any improvement upon variance. So, you know, if the pharmacy wants to switch, that's fine, but they shouldn't base it on this particular aspect of it. We will work through a couple more examples in the next video.